Good morning, ma'am. My name is Zamira. My roll number is 219518041. I am pursuing my first year EC in Institute of Aeronautical Engineering, Section B. Today, my topic is experimental and kinetic study of the Martian atmospheric entry plasma. Kinetic description of Martian atmospheric entry plasma. Abstract. A kinetic model for Martian atmospheric entry plasma is presented. The model was calculated based on data from Viking, Fatfinder, and the Mars Explorer rover Opportunity and Spirit. Calculations of the density, temperature, and the electron density across the shock front were made. We employed steady state and non steady state kinetic modules to describe the rate of dissociation of gases in the Martian atmosphere as well as the production of O2. Water vapor was included in the model science. It represents 0.03% of the surface atmospheric composition. With the addition of small amount of water vapor, we found a decrease in dissociation of CO2 in the Martian air as well as increase in the production of O2. This paper is to report analysis of MAEP and its interaction with the shock front which forms in front of the Martian landers. Introduction. NASA's Mars Exploration Program seeks to understand Mars as a dynamic system, including measuring the structure of the upper atmosphere and ionosphere, understanding the past and present climate and its potential habitat. In keeping with these goals, many satellites and landers have been sent to Mars. Each of these Martian probes and satellites face numerous challenges on their long mission. For the satellites, one of the most challenging perhaps phase is the air-broking phase, first used by the Magellan spacecraft while orbiting Venus in 1993 and then by the Mars Global Surveyor in 1997. The satellites skimmed at the atmosphere of the planet using the friction between the atmosphere and the probes to slow their velocity. This subsequently led to a decrease in the orbital radius for the satellite. The major benefit of this process is that the naturally occurring force were used to decrease the attitude of the orbit as opposed to a deorbital burn which would involve the use of fuel to initiate the engines. Since less fuel was needed for the mission to get the satellite into orbit, the cost was lower. The friction also caused heating and the ionization of the surrounding atmosphere, generating Martian atmospheric entry plasma MAEP, which is relatively poorly understood. The first report on hypersonic aerodynamic problems during terrestrial re-entry was apparently by Herman. He reported how the changes in the altitude and the strong heating at the stagnation point would affect the chemical composition of the air flowing around the probe and eventually cause ionization. And in addition, he decreased the interaction of the ionized gas with a shock wave formed by a circular cylinder, sphere, and circular cone. Although this paper was concerned with the re-entry, it helped to define the types of obstacles that the Mars exploration landers would face during entry. A more comprehensive review of the effect of planetary atmosphere entry at March number greater than 20 for Earth, Mars, and the Jupiter was given by GNOFFO. Martian entry plasma is a complex mixture constituting a numerous atomic and molecular gas CO2, O2, O, CO, NO, N2, CN, C2, NC, and ions C plus, O plus 2, AR plus, O minus, CN plus, O plus, CO plus, and NO plus. And electrons modeling of these types of plasma is very computationally intensive. Gor- Gorillot Alshot through a comparison of experiments and numerical simultaneous at shock speed of 4 to 9 kilometers that the model this type of discharge a weaker dissociation rate for CO2 modules has to be included in the module. In addition, they showed that for non equilibrium ionization behind the shock front, a slower ionization rate for C and O atoms by electrons impact and the non-equilibrium distribution of the free electron temperature must also be included in an earlier work by at ala thermochemical model using the previous identified molecular atomic and ionic species was used to show that the vibrational temperature approaches the translation temperature quickly behind the shock front. In recent years, there have been many models and experiments by using a thermochemical non-equilibrium Navier shocks slower. These researchers have shown how the rational temperature, vibrational temperature, number density, and molar fraction of the gas vary in a plasma or jet under specific laboratory condition. The main problem with these addition, they do not take into account the correct geometry for the Martian landers. This paper is to report an analysis of MAP and its interaction with the shock front which forms in the front of the Martian lander. This paper is organized as follow. In section 2, we describe the free stream density measurements for the Viking landers 1 and 2 and Pathfinder. In section 3, we describe the entry trajectory data and the calculation for the shock wave jump parameters for this probe as well as for Mars exploration rovers MERS opportunity and spirit. In section 4 we describe the electron energy distribution functions EEDFS for CO2 under Martian entry condition. We show the change in the electron dissociation temperature and dissociation rate coefficient for CO2 and O2. Section 5 describes the calculation of the electron density under jump condition for three Martian probes, given that the dominant neutral species in the MAP will be CO2, O2, O, CO, NO, N2, and AR. Inspection 6 we discuss steady state and non-steady state chemical kinetic models used for the simulation of MAEP. Finally, in section 7, we discuss the inclusion of water vapor in the module and how it impacts the dissociation rate of CO2 in the Martian atmosphere. The table is given below. Second, characteristic of the Martian atmosphere. Observation made by several Martian probe and satellites suggest that atmosphere at the surface is primarily composed of CO2 with minor composition of N2 and AR. The Viking lander contained two diagnostic tools. The first and these in the Viking upper atmosphere mass spectrometer VUAMS, which took measurement of the free stream atmospheric density, pressure, and temperature between 160 and 130 kilometers. The second is the Viking atmosphere structure instrument, which provided data from 120 to 9 kilometer. In the upper atmosphere, the VMS provided data about the composition changes from 200 to 110 kilometer. Based on this result, NIER and Macrol created a simple model for the number of species for each of the Viking lander. In table 2, we show the composition changes for the under atmosphere from Viking lander 2. From the table, we observe that composition changes greatly with altitude. At 125 km, the composition is comparable The composition is comparable with the changes greatly with altitude. At 125 km, the composition is comparable with the composition at the surface. Therefore, we will use the surface atmospheric composition for altitudes. Below 100 km above the altitude, we will use the result from the Viking landers. The graph is given below. Beyond the basic composition of the atmosphere, there is much information from the Pathfinder and Viking lander about the free stream density and temperature during the entry plasma into the atmosphere, this phase being at approximately 160 km above the space and last until the parachutes are developed for landing around 9 kilometers with a total elapsed time of approximately 120 seconds. The Pathfinder probe had three diagnostic tools, one set in each plant. During entry, each of these tools collected data from the density, pressure, and temperature for the entry plasma. The free stream density measurement for the Martian atmosphere, we observed that VR Viking measurements are higher than the Pathfinder measurements at higher altitudes. This difference is due to seasonal density changes and diurnal variation within the thermosphere. The two modules were constructed for the Pathfinder data using the altitude distribution. POE C1H1 were constructed for the Pathfinder data using the altitude a constant determination by calculation, and his the height is in kilometers. Free stream temperature measurements were made during entry by the Pathfinder and Viking landers. We observed that the temperature is very high in the upper atmosphere, which most likely is caused by solar radiation. The temperature then decrease with decreased altitude, reaching a minimum at 80 kilometers. According to Schofield, this temperature minimum may be due to superposition of waves such as thermal tides. These tides will be propagate from the lower atmosphere to higher altitudes with increased amplitude from 80 kilometers. This graph shows that altitudes raises and downs. For better understanding, these graphs are provided. Temperature once again begins to increase until it reaches an average of about 220 K at the surface. A comparison of the data from three probes shows that temperature measurements were less precise than the free stream density measurements. Two modules have been employed to estimate the temperature, the Gillen model and the Lagrangian atmospheric upwind relaxation algorithm. Neither of these was able to accurately describe the trend in the data. All of the data were collected of relatively the same time of the year and same distance from the equator. The only known difference in the data is from the fact that Viking data were taken taken 20 years before the Pathfinder data. For our research, we have estimated the average temperature over all sets of current mass data. The resulting curve is labeled present model. In addition, we have constructed an upper and lower limit for the temperatures, which can be seen as the shading in the calculation which involve these temperature measurements. Martian probe entry trajectory and shock parameters. By reconstruction the entry trajectory of main probes, when we use the present module, we are able to develop an accurate portent of all the atmospheric phenomena faced by them. We have constructed the velocity of measurement for each of the listed process. We note that the velocity was constant down to an altitude of 60 kilometers. The velocity then dropped sharply over the next 50 kilometers at an altitude of approximately 10 kilometers. As mentioned earlier, the parachutes for each of probes were developed due to the closeness to the more spirit and more opportunity data. We will We will use the more opportunity data for the remainder of this paper. These data will be have error bars to take into account the velocity measurement uh, of the Merce Spirit probe. Is important to note that although there are sufficient velocities data for reconstruction of the trajectory of the Mer landers, there are no free streams temperatures of density measurements for these landers. The Mach number m for each probe was determining by using where vs the velocity of the probe was csi speed of sound in the medium determined by cs the specific heat ratio RIS universal gas constant entered the atmosphere with peak values of 42, 31, and 25 for the Pathfinder, Mer Opportunities, and Viking Lander, respectively. Then the match number begins to decrease sharply due to the increase of atmosphere density. In order to accurate estimate electrons density and the gas comparison for MAEP, we must constant a simple module for the shock region in front of each probe during entry. For this model, certain assumption must be made. The gas mixture generated during entry and the thermatical perfect gas. Second one, ionization occur instantly behind the shock front. The gas mixture are constant in the boundaries layer behind the shock. Fourth one, a gas parameter are denied by the first stream parameters and our relations across the shock. From these assumptions, we are able to calculate the shock parameters where it's the specific heat ratio, the oblique shock angle. This TIS, the atmospheric temperature, from the PIS, the atmospheric density, the calculated density across the shock layer or jumping density, and we calculated these values from which the specific heat ratio of the Martian atmosphere is 1.29 and the oblique shock angle for the three probes was 78.9 degree. The jump temperature was calculated. We observed the temperature reaches a peak average value of about 36,000 K, 90,000, 19,000 K, and 13,000 K for the Pathfinder, where Opportunity and Viking landers, respectively. These maximum values are curated between 50 to 60 kilometer above the surface. The shaped region give a range of values for the temperature. For example, the Pathfinder has a peak temperature of 36,000 K plus 25,000 around the 60 kilometer higher altitude. All the distributions become a wider since the atmosphere becomes less dense. Fourth, evolution of EEDF. In the absence of magnetic field, the flow of electrons through until velocity passes space are described by the Boltzmann transport equation. Here, the distribution of electrons in their velocity space at the space coordinates and the time given by the electron velocity distribution function and EIS charge of the electron. In case of weakly ionized gas, the right hand side of will take the account of elastic and inelastic between electrons and neutral atoms or molecules to the complexity. Solutions can be determined for selected cases. We have employed the approximate for our model, the homogeneous approximation, the steady state approximately where the electrons conclusion frequently in the ionized gas is approximately 2 or 3 orders of magnitude ladders than the drive frequency and symmetric along an axis of symmetric for the Martian probes. By applying this approximately a steady state isospheric solutions can be obtained for a monoatomic gas. Here we expressed by convention the solutions in terms of the electron energy E is equals to mv2 by 2 and have neglected super elastic conclusions in QMS. In QMS, the moment transfer cross sections quiz, the cross sections of the elastic collisions EIS, the electric field N and trace mass density and the temperature of neutral gas molecules at the Boltzmann constant and the FIS isospheric gas mixture approximately modifies the cross sections of all gases species in six should be made. The first term and QM The second and the third terms here coins the moment transfer cross sections. GNIS the mole fractions and the MNIS the mass of the molecule of the nth species were calculated the EDF by applying the commercial numerical Boltzmann slower for the values of the ridiculing field, and an upgrade version of Balt 6 known as Balt 6 provides a similar result as the old Balt 6, but allows for more species including in the calculation of the discharge parameters and the EDF. The EDF values we are able to calculate the average electrons temperature. The equations are given below and graphs are shown for the better understanding. By applying 7 we calculated the average electron temperature at various values of E by N for terrestrial air and Martian air and present these results in figure 8. We observed that tin or increase we observed that increase almost linearly with En values greater than 4 into 10 into minus 16 weak centimeters below the point. The values for terrestrial air increase very slowly and are more almost constant, while the values are Martian air constitute increase linearly. This dissociation rate coefficient more CO2 and O2 were calculated by employing 8R shown in the figure. We note that the coefficient increase strongly with the reduced electric field. Fifth one, evolution of electron density. The electron density was evaluated by using the Shah equation, where Nik is the number density of ions from species K, and K is the neutral species density, IKS the ionization potential, O species K, GKIS the statical weight of the ion species K, and GKIS is the statical weight of the neutral species. The model we have assumed that the electron per temperature equilibrates to the gas temperature obtained in figure 6. We must also assume that the temperature is still high enough that we can neglect the effect of ion chemistry. In addition, we are not including the free stream electron density, and the equation is given below. Thank you for giving me this wonderful opportunity. I end my topic here.